Hello and welcome. I hope you are doing great. In this video, we are going to discuss about Markov's inequality, Chebyshev inequality, and Chernoff bound. So I hope the screen is visible. Let's set up the agenda first. So we'll discuss about Markov's inequality. So that's the base inequality. Okay. So this is the base. And the next Chebyshev inequality is an improvement over Markov's inequality. And the Chernoff bound is an improvement over Chebyshev. Okay. So let's understand what problem they solve and how each one is an improvement over the other. So Markov's inequality is the base. Okay, that's the base intuition. If you understand this, we'll spend some time understanding this, and then everything will follow, and there will be like incremental changes. So, and the understanding remains the same. So let's start with Markov's inequality. So the first one is Markov's inequality. So let's understand this with a simple example first. So let's understand why are we learning this again. So as in all the videos or all the concepts that we are understanding. So we'll start with the why. Why are we understanding this? Suppose there's a problem. Okay, so you have a sample and you have the average height of that sample of people. So you've collected a sample of say 100 people, and the average height comes out to be 150 centimeter. So now the question is, what is the probability of finding someone of height 200 centimeter? That will be very low, right? And if I say, what is the probability of finding someone of height 250 centimeters? That will be even lower. So what do we understand by this? That if the expected value or the mean is low, then the probability of finding a very large value will also be low. So the people are 150 centimeter on an average tall, then finding someone of 6.5 feet, 7 feet, or even higher is very low. As you move away from the mean, the probability of finding that will become even lower and lower. So that's the main intuition behind this. So the next question is, if I ask you to tell me, can you give me an upper bound of the probability? Say for example, if I tell you the average height of a sample is 150 centimeter, can you give me an upper bound of the probability of finding someone whose height is greater than 200 centimeters? So that's what Markov's inequality gives you. Okay, so let me tell you the exact definition. Okay, what is it? So Markov's inequality gives an upper bound. It gives you the upper bound. Okay, for the probability that a non-negative random variable will not exceed given the expected value. So you have the expected value of a random variable, and the Markov's inequality gives you the upper bound. Beyond that, the probability of finding some value will not exceed. It gives you the upper bound of the probability. So let me give you a formal definition for this. So what is Markov's inequality? So this gives an upper bound of the probability, upper bound for the probability. I am writing whatever I said. Probability that a non-negative means greater than or equal to 0. Non-negative random variable, okay, will not exceed. So this gives you the upper bound. Beyond that, the probability of a given value won't exceed given or based on its expected value. Okay, so formula for this is, so probability of finding some value that is greater than or equal to a is less or equal to the expected value of x by a. So this a and this a are the same value. So divide the expected value by a, and this gives you the upper bound, that the probability will always be less than or equal to this upper bound. So this is what is Markov's inequality in simple terms. So a note is that it gives you a very loose upper bound. I'll explain you what is this loose upper bound with an example, so that's when it will become clear. But before that, let's see a good example, okay, to understand this in more concrete way. For example, I'll give you a question. For example, a restaurant expects to serve on an average 50 customers per hour. So what is the probability to expect more than 200 customers in next 1 hour? Okay, so let me write it down. A restaurant expects to serve on an average 50 customers per hour. So given this, so your average is expected value. So what is the probability that they will serve greater than or more than 200 customers? Greater than or equal to 200 customers in next 1 hour. So directly this is based on a formula. So we know that. So let me copy this as it is. We know by Markov's inequality that probability of x greater than or equal to a. So let's put the values here. So here expected value of x is equal to 50 and a is equal to 200. So let's put this. Probability of seeing greater than or equal to 200 customers will be less than or equal to 50 by 200. This is equal to 1 by 4, that is 0.25 or 25% chance that they will see greater than or equal to 200 customers. So this is a very loose upper bound. So anything that is the max probability, whatever probability that will be there in reality will be less than this 25%. Okay, but this is the upper bound, that's the upper limit of this probability. So let's see one more example to understand, and this example we'll use again. So this is with respect to marks. Okay, so marks data, marks in a test. So consider a test where average score is equal to 70 out of 100. Okay, so my question is, what is the probability that a randomly selected student gets greater than 90? Randomly selected student scores greater than or equal to 90 marks in the same test. You have to find this. Simple, same formula. Now here, what is the expected value of x? This is equal to 70. Okay, and probability of x greater than or equal to 90 is less than or equal to expected value by a. This and this value will be same. This is your a here. A is 90. So this is equal to 7 by 9. This will be like 0.777, something like that. So approximately you can say like 78% chance. But this is like very, very high. So that's why it's called like that. The maximum probability of finding someone with 90% marks when average marks is 70 is less than or equal to 78% or 0.777. Okay. So we'll solve this problem again using Chebyshev inequality. I hope Markov's inequality is clear. Here, nothing is given about this. So the most important thing about Markov's inequality utility is that we know nothing about the distribution, just the expected value. Okay, just the expected value, and it will give you a loose upper bound. So this is very, very helpful for finding sometimes what will be the upper bound of some probability. Okay, no information about the distribution, nothing else is given, only the expected value, and based on that it is giving us the upper bound, and that's very helpful. Okay, I hope Markov's inequality is clear. Now let's build on top of this and understand Chebyshev. So Chebyshev did nothing but he improved this. So this used Markov's inequality and improved it. Okay, the intuition behind Chebyshev's inequality is that, so probability of say for example this Chebyshev. So the important thing about Chebyshev is that if I have the data and I have mean, it also uses the variance. So it also uses a plus mean plus variance, and based on that the intuition here is the probability of finding a random variable away from mean. This is the mean. So finding any random variable away from mean will be low if the variance is low. If the variance is low means everything is closer to the mean. So probability of finding something away from the of finding a random variable's value away from the mean will be less if the variance is less, and that's the central theme about Chebyshev inequality. And it also uses variance in addition to mean or expected value that was used by Markov's inequality. So that's what it added, one more information, that finding anything away from the mean would be less if the variance is less, and it is using an extra information, that is variance or the second moment. This is first moment and second moment. Okay, so let's write down the formula. Also it doesn't assume so there's one more thing is that does not assume that a random value is non-negative, that a random value is non-negative. It is applicable for both negative and positive because it uses something called mod. So what is variance intuitively? So variance is nothing but square of distance from mean, right? This is, sorry, what was variance? So let me write it down. Variance of x, remember, right? This is expected value of x minus whole square, that is the distance from mean. So this was a variance. So using this, you will see that it is using the same concept. Chebyshev is using this distance from mean, and it is based on that, and it is using that formula. So this can be derived. I will skip the derivation part, just give you the utility. So this was for intuition. So what is Chebyshev inequality formula? A probability of finding, okay, something away from mean, okay, is less than equal to the expected value of x minus expected value of x whole square by k square. So this k and this k is same, and if you see here, right, okay, if you see the similarity, this x here is kind of replaced with distance from mean, x minus expected value of x. This is your mean. So if you replace, it is using one more step ahead, going step ahead, and it is replacing this x with distance from mean, x minus ex, and it is using the same. So one side, and this mod is because if you take square it, and sorry, in the derivation, if you square it and if you take the square root again, so it will give you plus minus, and this is the mod for that, and the other side is only, this is squared for the distance of mean. So that is the intuition of the derivation, so that when you look at the derivation, okay, if you're interested, then you will understand the theory, why it is so. Okay, and we know that from here that this is your variance, sorry, this is your variance, this whole value, we can simply replace it with variance. So we can rewrite this as, this implies probability of distance from mean to be greater than equal to some value k is equal to variance of x is less than or equal to variance of x by k square. So probability of a random variable distance from mean being greater than or equal to some value is less than or equal to its variance divided by that k square. This is how it is read. So let's understand it with the same question that we saw. This one. So copy paste. Let me make it small. So this is the question. Let's use the same question to illustrate that how Chebyshev inequality gives tighter bounds. So it's the same question that we'll use. Oh, why didn't copy? So let me copy it correctly. Copy. And let me paste it. This is the question. But we know that Chebyshev inequality also needs the variance. So given that 90 meters and 90 marks given, variance is equal to sigma square is equal to 100. So this is given now because Chebyshev also uses variance. It uses mean plus variance. So how will this work out now? So we know that from Chebyshev inequality, the probability of finding something, the distance from the mean greater than or equal to k is less than or equal to variance of x by k square. Now, so we have expected value of x that is equal to 70. What will be k here? So it is not a direct. We want to find that the marks expected was a was 90. So how do we do this? So if we say that mod of x minus expectation of x 70, okay, it's greater than or equal to this k is 90. So this is distance from mean, right? And I want this 90. So what is the distance from mean for 90? So 90 minus 70, that is 20. So this is giving him the distance from mean. So if I say greater than or equal to 20, can I say this? Can I say this? So this is equal to, this mod gives me the range of values on plus minus side, right? So this means that distance from the mean, so this is my mean 70 on both the sides. So this is my mean. So distance on both the sides. Let me draw this line, okay? So this is my mean 70. So if I go plus minus 20 plus 20, this is what mod means. So this will range between minus 50 to, so this is my mean. This mod will give me the plus minus range, okay? This will vary from, so if I go to 50 or 90, still that value, the distance from the mean will be in that 20 range. So I want the 90 value, so I'll use the same value. So this can be rewritten, this thing can be rewritten in this way. So probability of mod of x minus 70 greater than or equal to 20 is less than or equal to variance of x is 100, and now my k here is 20. So here my k becomes, this is my k. So since k is equal to 20, this is my k, this is my k. So what will be this value? So this will be equal to 100 by 20 into 20, 25 times 5 4 times, this is equal to 1 by 4, that is equal to 0.25, that is approximately equal to 25%. Now you see here, I'm getting that the probability of finding someone who has scored 90 marks or greater is 25% using Chebyshev inequality, and we got this as 78% here. This is 78%, and here this is 25%. So that's why we said that this Markov's inequality gives very a loose upper bound, that this will be less than or equal to 78, but this is very loose, that it is, if it is, it should be the, I don't know what would be the right value. Say if it is like 20% chances, so it is giving you 78%, but 20 is less than 78, but this is very loose. Now Chebyshev is giving you even tighter bound, that it is less than or equal to 25%. So it is very close to your actual, but it is giving your upper bound. It won't give you the exact value, but just based on the expected value, that is mean and variance, it is giving you the upper bound of that probability. This is very, very powerful. It is used in application just to find, without knowing anything about the distribution, just using the mean and the variance, that is the first moment and second moment, we can get the upper bound of any probability of a value of being how far it is from the distance from the mean. How far is that distance? Okay, so that will give me the variance. If this is the mean, how far is the value? And as this value increases, the probability will decrease, because this k value will increase and it will be proportional to k square. Here it was proportional to just a, that is distance from, that is just the value of x square value, and then this is distance from mean, and this is degree of k square. That's why it is giving a tighter bound, because this will grow faster than a linear a. Okay, I hope this is clear. So Chebyshev inequality is clear. Now let's move to the next concept. Okay, that is Chernoff bound. So this is just an extension on top of that. So Chernoff bound goes even a step further, but this is not generally used as we were using Markov and Chebyshev inequality. This has a special use case. So this is generally used, okay, when this is used for sum or average. This is used for sum or average, whenever the sum or average is required. Here we are going for exact values, but here we are going for series of values and series of sequence of random variables, and we find the sum or average, and we want to find what will be the upper bound for that sum or average. Then we use Chernoff bounds, and there we get a very tight upper bound, and I'll tell you the reason why in some time. Okay, used for sum or average of independent random variables. So all the random variables must be independent, so they not be identically distributed. So we remember IID. So they should be independent, but need not be identically distributed. So this is for a sequence of random variables, right? So we'll have x1, x2 till xn. So they are independent, but need not be identically distributed. So this is applicable for that Chernoff bounds. Okay. So this is based on MGF. Remember MGF? Moment generating function. So moment generating function, if you remember, it generates the different moments of a distribution of a random variable. So the first moment is called mean, second moment is variance, third moment is skewness, fourth moment is kurtosis. You remember all this, right? So this uses moment generating function, and that's how it is giving even tighter bounds, because it is using more information about the distribution. So whatever is the distribution, right, whatever is the curve, it is using more information. So Markov's inequality used only mean. Chebyshev went a step ahead, and it used first two moments, mean and variance. And the Chernoff bound is going even a step further, and it is using all the moments, okay, using the moment generating function. And that's how, because of that, it has more information about the distribution, how the curve is, because we know that first one gives the mean, gives the central tendency, second one variance gives the spread of the data, third skewness gives me the asymmetry of the data, whether it's left skewed or right skewed, and the kurtosis gives me the tailedness, that how fat or thin the tail is, and depending upon that we get the outlier. So this gives me the information about the shape of the distribution, and this uses more information, because of this moment generating function, more information about the shape of the underlying distribution, whatever distribution it is. And that's how it is able to get, because the more information you use, more better approximation you can make of the upper bound of the data. Okay, and how is it given? What is the formula? So this tells me that probability of x greater than equal to c is less than equal to expected value of e to the power tx by e to the power tc for all t greater than 0. So t is positive. Okay, same as in the this is, and we know that this is what is this? This is your MGF, moment generating function. This one. And now you see in the denominator there is e to the power tc. In Markov's we had only one, power 1. In Chebyshev we have k square, that is quadratic, second degree, and this is e to the power t, this is exponential. The exponential curve rises more sharply. Okay, it has got a more sharp rise. A quadratic curve will rise slowly. This will be like that. Okay, or it will be like this. It will rise slowly, but exponential curve rises very fastly. Okay, this will be a quadratic curve. Sorry, this will be your quadratic curve like this, but an exponential curve will rise very fast like this. That's why it converges to a, means it gives a more tighter bound as the value of x increases. Okay, but again if you see, this is the extension of the Markov's inequality itself. They have just do a rehash or even more processing of that and use the moment generating function. How is it that? So let me give a brief intuition around that so that you can check the derivation later. So we can say that, for example, if p is a probability of x greater than equal to c, can we say that this is equal to probability of e to the power tx greater than equal to e to the power tc? Can we say this? Given, okay, provided or given that t is positive. If t is positive, so if you have x and c, so any power of e will be higher correspondingly. E to the power x, if x is higher, say for example x is equal to 1 and c is equal to 5. So e to the, if 1 is, sorry, other way around. If x is equal to 5 and c is equal to 2, so 5 is greater than equal to 2, we can say that. Similarly, e to, I don't know if it's visible. Let me cut it off, bring it here. For example, x is equal to 5 and c is equal to 2. So we can say that x is greater than equal to 5, x is greater than equal to c. Similarly, e to the power 5 will be greater than equal to e to the power 2. If it is greater than, remove the equal to. So that's what is the property we are using here. And t is positive means the product will also be positive. Okay. So this is the intuition behind this. So what is this? Now let's put it here using the Markov. What was the Markov's inequality? It's just nothing but a rehash of that. We are just processing. So this is from Markov's inequality. Okay, and let's replace this x greater than equal to c with this information. Let's replace this x greater than equal to a or x greater than equal to c with this equivalent expression. This will be p of e to the power tx greater than equal to e to the power tc is less than equal to expectation of e to the power tx by x is replaced by e to the power tx by e to the power tc, and this is nothing but our Chernoff bound, and this is also your MGF, moment generating function. Okay, I hope this is clear. So in this, and sometimes it is also written as in the short form, right? This can be written as probability of, so this is the intuition for your derivation. You can check the proof. Probability of x greater than equal to c is given by less than equal to it. This comes up and it is written in this way. in this concise way without the denominator. Also, when it is summation, right? So sometimes in the summation form it is written as, it is, as I mentioned, this is used for sum in the sum or average of independent random variables. So how is this sum? In that sum formulation, it is written as probability of sum of n random variables to be greater than or equal to c is less than or equal to e to the power minus tc, and this moment generating function I'll write it as m of x of t. Okay, and this whole n like that. This is your MGF. This is how your MGF is defined. MXT is this. So this is the symbol you will see somewhere in the notebooks. So this is your summation till n. This is your sum of n RV random variables, independent random variables. Okay. I hope Chernoff bounds is also clear. And because of this, as I mentioned, right, why is it, how is it giving tighter bounds? Because it gives, so this gives it gives exponentially tighter bounds because of the exponential function in the denominator, e to the power tc, better, which is better than Chebyshev inequalities quadratic bound, quadratic decay. So it is the denominator, right? So that's what it will decrease it. So the value will decrease, as I mentioned there. So I showed you earlier too, that the quadratic function increases slowly than the exponential. Exponential grows very fast if you plot the graph. Okay, so that's all for this video. Let me quickly summarize that so that you know all the connection. It's quite easy. It's easy. So we went through. So in today's discussion, we are discussing about Markov's inequality, Chebyshev inequality, and Chernoff bound. So this is the use cases when you have an average, okay, or average of a number and expected value of a number of, say, for example, a height, and we want to find that for that if the value is greater than some value. Okay, for example, if the height of a given sample is 150 centimeter and you want to find the number of, or the probability of finding someone who is greater than or equal to 200 centimeter. So this is what Markov's inequality gives me, and it does not take into consideration what is the distribution, because if you have the underlying distribution, then we can find a lot of information, but the only thing information that we have is expected value, and that's what it uses to give me a very good approximation of the upper bound of that probability. And it is given by probability of finding an x value greater than or equal to a will be less than or equal to expected value of that x divided by a. This and this a is same. It gives me a loose upper bound. Then we saw some examples, and it just uses the expected value or mean. Then we saw Chebyshev inequality, which uses mean plus variance. It's an advancement over Markov's inequality, and it does not assume that random variable is not non-negative. This was defined for only non-negative values. And we saw that this is the formula here, the probability of finding any number or distance from the mean to be greater than or equal to x. This is a modular, so on both the sides of the mean, that's what makes it non-negative, is less than or equal to variance of x given by k square. So this k square is quadratic here, and this k are same. Okay, so it uses first and second moment, mean and variance. And then we saw using an example that how for the same problem it gives a better upper bound, a tighter upper bound. That is, it gives me the 25%, which is better than 78% chances of finding something greater than or equal to 90 marks. Then we took a step further and went to Chernoff bounds, which is a further extension. This is generally used for some or average of independent random variables. Okay, it does not have the same use case, but uses the same concept. Okay, and this is based on moment generating function. So what is the moment generating function? Because it uses moment generating function, it uses more information about the shape of the underlying distribution, because each moment brings some information, right? First First moment gives me the central tendency, second moment is variance, that gives me the spread, third moment is skewness, that gives me the symmetry, whether it's symmetric, asymmetry, okay, whatever it is left skewed, right skewed, and the fourth, these are the four important moments, and the fourth one is kurtosis, which gives me the information about the tailedness, how fat or thick the tail is, and how many outliers are there. So these are the four moments that we use, and depending upon that, because it uses more information, it gives a even more accurate or a better, tighter bound for the upper bound, means value for the upper bound. And it is just an extension of Markov's inequality. We saw this with the help of an example, and then this is the formula here. The probability of finding x greater than or equal to c is less than or equal to e to the power minus tc, expected value of e to the power tx, which is the moment generating function. We also saw the summation and the summation formula for this. Okay, I hope Markov's inequality, Chebyshev inequality, and Chernoff bound is clear. Okay, that's all for this video. Thanks for watching. Have a good day. Bye for now.